Hello, everyone. This is Steve Palladino from Palladino Power Project, and I'm bringing you a video this time on a dashboard that I made for WKO software for running, and it's called the FRC and VO2 modeling dashboard. And I'm going to do actually three videos of what I plan to do on this. First one, this one is going to be focusing on this chart right here, the primary workhorse of this particular dashboard. So I'm going to focus on that, some of the underlying concepts, and how the chart works, how to read it, and then I will start getting into examples in the subsequent videos. Just a brief overview of the dashboard. Again, the primary focus is this chart right here, but I also have a couple of reports built in. And one of them is just a report that constructs the time at 100% or 95 or 90% of quote unquote, I don't have quotes there in writing, but power at VO2 max. So quote power VO2 max. I say quote power at VO2 max because there is no single power at VO2 max. Now, often when people say power VO2 max, it is typically the highest power that will elicit VO2 max. And the same thing with velocity of VO2 max is often used when they're actually referring to the highest power. But you can elicit VO2 max. It depends on the slow component of VO2. You could elicit VO2 max at lower power, that is above your critical power, above your functional threshold power, and you reach a certain threshold where if it's held long enough, you can eventually elicit VO2 max. In other words, VO2 goes up and up and up until it hits max. So that is the beginning of that band of power duration pairs that will elicit VO2 max. On the low end, it involves a slow component, and on the high end, it's a much faster VO2 connects getting to VO2 max, and that's the highest power at VO2 max. So that's sort of some of the underlying VO2 part of it, but I'm going to come back to this and how we model this as best we can with power. When I say we, I mean me, as I look at it, and I've developed this particular chart. And the report has some other features in here that I'm not going to go into at this point in time. And then it also has this little report that tells you during a particular workout what was the lowest FRC, how much of the FRC was used. And let me go on that little tangent here. FRC in WKO stands for functional reserve capacity. I often use the term, and I prefer to use the term, reserve work capacity. Reserve work capacity. These are all terms that are being applied to the same concept, and that is W prime, FRC, in exert, it's high intensity energy, HIE, and my preferred term or acronym is reserve work capacity, RWC. They all are referring to a similar concept. The amount of work that an athlete can do in excess of FTP in a single bout of exercise. So if your FTP is 300 and you're running an interval at 310 watts, you are using that reserve work capacity because it's over 300 watts. So you have this extra reserve, which is based on both aerobic and anaerobic metabolism, but you have this extra reserve of work that can be done when you exceed critical power or functional threshold power. This particular report tells you how much you used up of that FRC or reserve work capacity. This athlete's reserve work capacity is 6.8 kilojoules, and in this workout had used up pretty near 100% of it at the later stages of the workout, and got down to theoretically 0.03 kilojoules left in the tank, so to speak, of that reserve work. So there's a couple reports here in this dashboard. Also, I have a couple other charts. This is a chart that uses the Skiba 1 W prime balance model. Just for comparison's sake, and you can see this one, I believe this one to be superior after using it long enough and comparing them. You shouldn't see overshoots of 0 kilojoules, as I highlight that right now. There's 0 kilojoules, and you can see that it's overshot that 0 kilojoules. Not good. That's that. In other words, the model is very good, but I found that in our applications here, it does not perform as well as this model up here that I'm going to go into in more depth in just a moment. And then I'm going to come back to these lower two. The lower two is just a way of checking the FRC, the dynamic FRC part of it. So let me come back up here and enlarge this chart because I want to focus on that just a little bit. So there you go. So this chart is at the center right here, this horizontal line, it represents 100% of power at VO2 max right here. It also represents 0 kilojoules left in that reserve work capacity. So you have this reserve work capacity working down towards 0, and you have percentage of power at VO2 max working upwards towards 100%, meeting in the middle in some cases. So that's how the chart is constructed to look at. So again, FRC working down to 0 and percent of power VO2 max working up to 100%. All right, so let me talk about the percent of VO2 max. I mentioned earlier what quote unquote power VO2 max might mean, and it's not a single power, there's a range of powers. In this chart, what I use is I use the individual's modeled 5-minute power. So the WKO power duration model 5-minute point, that power, the modeled 5-minute power, is my surrogate for quote unquote power at VO2 max. It's obviously it's not going to be accurate for every individual, but it's going to be pretty close. Time to exhaustion at VO2 max across multiple studies generally ranges from right around 4 minutes to maybe 6 minutes. Yeah, there's a few that are longer, and those are probably more elite athletes that are extending time to exhaustion at VO2 max into the 6 to 8 minute range. But by and large, 4 to 6 minutes is the range of most human trained athletes, runners, that is. Human trained runners. So 5 minutes, I found, because I've formerly used 6 minutes, and I found that not to model things well enough. That power represents a lower power than what is likely power VO2 max across a broad swath of individuals. I've turned the model down to the 5 minute, or up to the 5 minute mark, the higher power in essence, lower duration, higher power. So I found that the 5 minute model power works pretty well. Now, for most individuals, let's say they're 4 minutes and 15 seconds, not 5 minutes, the percentage difference in that power is not huge. Same thing as, let's say they're a 5:30 versus 5 minutes is their time to exhaustion at VO2 max. Then again, the difference is not that big in that little range of durations. Yes, there are differences, so it's not perfect, but it's pretty close. And I found that the 5 minute modeled power in a optimized power duration curve. All right, so you have to have some testing done in the 3 minute, 2 minute, and less range, and you have to have some testing up there in the 10 minute and longer range, and that will make the model fairly well optimized, such that your 5 minute model power becomes a reasonable surrogate for quote unquote power at VO2 max. So in this individual, their 5 minute power is this: power at VO2 max, 353 watts. The individual's FTP, the set FTP, I like using set FTP because there might be little nuances in what the model FTP is. In most of the individuals that I coach, set FTP or SFTP, run FTP, is the same as model FTP. I use the same. But there's a few individuals where it might be a couple watts here, a couple watts there. I use the set FTP for this chart here. So notice there's a blue line here. The black line here, if I come over here, see the black lines? Though that's power. That's the actual power recording from the fit file. The blue line is percent of power at VO2 max. Percent, it's abbreviated here, but it's percent of power at VO2 max. This is based on a 25-second exponentially weighted moving average of power. Again, a 25-second exponentially weighted moving average of power. Why? Because, and this is taken straight from Dr. Andy Coggin, 25-second exponentially moving average of power best represents VO2 kinetics. So when you start an interval, your power is up here, but it takes a while for the VO2 kinetics to catch up. So the exponentially weighted moving average of power is a better reflection when modeling the percent of power at VO2 max down here. So that's how I come up with the blue line is based on an exponentially weighted moving average 25-second of power. So there you have it. You have a based on power data only. So there are assumptions. Again, it's not perfect, but it's in my experience has been pretty close that it makes it useful. Again, all models are wrong, but some are useful. This is a perfect case of a model that's probably not perfect, but is useful to me as a coach. So that's this side, the blue side. So when we follow this particular workout, we can see percent of power at VO2 max as the blue line. And I have some little crosshatch line, horizontal lines here. The lower one is 90% of power at VO2 max. Then the next one is 95% of power at VO2 max. And then right here at the middle is 100% of power at VO2 max. So there you go. That's reading that particular side of the chart. On the other side, we use WKO's dynamic FRC model. So again, remember you have this reserve work capacity. Some people like to use the tank analogy where you start dipping into the tank and draining the tank as you exceed critical or exceed FTP. So I'm going to come back here again. There's power. So if we look at just the power, we can see that in those 5 intervals that you see in the middle, not the 4 accelerations right before that, but the 5 intervals in the middle, you can see that the black power recording is above that set FTP of 334 watts, that horizontal line, which is right here, set FTP. And then we go back, look at the power. See, once we exceed FTP or critical power, once we exceed it, boom, power goes up and FRC starts dropping. In other words, the reserve work capacity, we start dipping into that tank. Once we dip into it, the only way to get it to come back up to baseline, the original full reserve work capacity or the full tank, is by resting. We got to go below FTP to allow that reserve work capacity to start coming back up. So here we are back above FTP again, reserve work capacity starts dropping. We get to recovery and reserve work capacity starts refilling itself, so to speak, reconstituting itself during recovery below FTP. So we're up above FTP up here in power, and that tank is getting drained. As soon as the power drops below that FTP line, FRC starts coming back up. Okay, so just a side note on dynamic FRC. Again, some of the early models were developed by Dr. Skiba and other co-workers. And that's this. In fact, Dr. Skiba's had a couple of different models. WKO came up with the dynamic FRC model. And when it's default, when you get it in WKO, it defaults to this. It's based on modeled FTP. So if you go and look at the model, remember it's really what your FTP is very important. And because when you're above it, you're draining the tank, and when you're below it, you're refilling the tank, right? So the default that comes with WKO uses FRC, a power duration metric that's provided from the power duration curve, and modeled FTP. Again, it's similar to auto CP and stride. Modeled FTP is the model from the power duration curve FTP. That's the way it defaults. But you look, the problem here is it overshoots zero. Zero is right here. There's FRC. There's dynamic FRC. And see how it overshoots zero? That should never happen. Theoretically, you've got only 6.8 kilojoules. So how can that happen? Either you haven't optimized the model on the far left-hand side such that FRC is underestimated, or your FTP is underestimated. One of the two will cause this to overshoot. I changed the model to one that's based on run FTP or set FTP. Notice it's the FTP model is 330. Based on various testing and racing, I think his FTP is closer to 334. So this model is based on set FTP, run FTP that you enter into WKO. This one's based on the model. So you can see this one hits 0.03 kilojoules in that fifth interval. So I think this is better by using set FTP. I still use FRC, assuming that I have an optimized left-hand side of the power duration curve. Ideally, for both of those numbers to be right, you want to have an fully optimized power duration curve. So again, that's a little side note, a little tangent on how I construct this FRC, dynamic FRC model. And let's go back and look at it again. So here is dynamic FRC based on your set FTP and your FRC from the power duration curve. Set FTP that you set and FRC that is provided by the power duration curve. So again, we can see that dropping down as we exceed FTP. So we have a situation where we're coming up and we're getting close to 100% power VO2 max in each interval. And the recovery periods, we squeeze those down, and that'll be another video. This is with 2 minute and 30-second recoveries, 3 minute intervals, 2 minute and 30-second recoveries. At one point in time, he was doing 3 minute intervals with 3 minute recoveries. And I'd see this coming up a little bit too much, and we never really touched down here. So I started squeezing down those recoveries a little bit, and we got to where we got to sort of a tap out point where there's no more reserve work capacity. That's done. The only way to reconstitute it. Look, this happened at roughly an hour in, right? And we weren't back until over 15 minutes later, maybe 17 minutes to fully reconstitute that. So it would take some time before you can squeeze any more intervals, and whether that's even wise is a whole nother matter. But the bottom line is we got a pretty good workout here. So we've talked about what these are here. Those are just horizontal lines representing percent of power VO2 max, and you can see that we're in between 95 and 100 right here. All right. If I want to know exactly, I could just use the scroll line. I could see that we're at 98% of VO2 max up here, up on top. We're at 98% of VO2 max and 91% of FRC used at that, running at that target power. Down here we have some summary metrics. So for this entire workout, he had only about 22 seconds where this modeling shows that he was at 100% of power VO2 max. You can't really go greater than 100% of VO2 max. I mean, you can go greater than the power, but you can't really go greater than 100% of VO2 max. 22 seconds. And about 10 minutes and 30 seconds were spent between 95% and 100%. So again, this horizontal line and this horizontal line, between those two right here. So he spent about 10 minutes and 30 seconds in this really prime area that I believe is important for getting appropriate adaptations near VO2 max. This one's less important, greater than 90% of VO2 max, I mean 13 minutes, but that's not the adaptation I was looking for. I was looking for greater than or equal to 95% in this particular workout. So we got 10 minutes and 30 seconds, and that was off of 15 minutes of intervals. So that's an efficiency of about 66% during that time right there. Over here, this is for the whole workout. These are the average power for the whole workout was 258 watts. The percent of power of VO2 max on average was 73%, and percent of set FTP was 77%. Now, if I click over here, and I'm going to click on just one interval, you can see for that interval that he averaged 353 watts, which was equal to his 5-minute power. So we're going to call that 100% of, he reached 100% of power at VO2 max. And that was also 106% of FTP for this particular athlete. So this is summary. This is summary for whatever range you select in the right-hand edge of, or right-hand explorer of WKO, whether it's the entire workout or just a single interval. And these are summary. This is for the entire workout. That doesn't change. Well, actually, it does. So this is interval number 1. That's where he got his 22 seconds, greater than 100% of VO2 max. But overall, for the whole workout, that's what I want to look at. All right, so there you go. The ways to read this chart, some of the background behind the chart, and hopefully that gives you some background. So then in the next couple of videos, we start looking at some workouts and dissecting them a little bit more. Thank you for watching. See you next time.